Hi and good day everyone. We are from session 1 and group 1, also known as the group of momentum. Because today we're going to present our assignment 2 for DMID Thermofluids, and our topic is momentum flow analysis. So first of all, our group consists of 5 members. I'm Darshan and my teammates are Amsha, Muazzamin, Hamirul and also Wan. Moving on, we've chosen this fire hose nozzle as our application, which is a critical tool in firefighting. Specifically, we studied the Acron brass adjustable nozzle, which is 35 centimeters long with inlet and outlet diameters of 4.5 centimeter and 2.5 centimeter respectively. It is designed efficiently to convert pressurized water into a high-speed jet. The sudden change in momentum generates a strong recoil force that firefighters must be able to control. These nozzles are used across municipal, industrial and military sectors and typically cost between Rm 500 to 2000. We chose this system because it clearly demonstrates fluid mechanics principle in real world context. Thank you.
Thank you, Darshan. Now I'll be explaining the mechanism behind the fire hose nozzle and how it relates to momentum flow analysis. Firstly, the working principle. The fire hose operates based on the conservation of momentum. Pressurized water flows from a hydrant or pump into the hose and then exits through a narrow nozzle at a much higher speed. Due to the continuity equation, when the nozzle gets narrower, the water speeds up. This fast-moving jet helps deliver water over long distances, but according to Newton's third law, this creates an opposite reaction, force, a recoil, which pushes back on the firefighter. Now, let's look at the working fluid. In this case, we're dealing with water, which has a density of 1000 kilograms per cubic meter and a viscosity of about 0.001 Pascal seconds. The speed of sound in water is around 1500 meters per second, which we use later when calculating the Mach number. Next, we apply the momentum flow equation, which actually tells us how to calculate the recoil force. We first find the mass flow rate, which actually depends on the water's density, the cross-sectional area of the outlet, and the velocity of the water exiting the nozzle. Let's go through a sample calculation. We assume that the inlet diameter is 4.5 centimeters, which gives an area of about 0.00159 square meters. The outlet diameter is smaller, 2.5 centimeters, which results in a smaller area. We also assume that the water enters the nozzle at 5 meters per second. Because the outlet is narrower, the water speeds up. Using the ratio of the inlet and outlet areas, we find that the exit velocity increases to around 16.22 meters per second. Then, by multiplying the water's density, the outlet area, and the outlet velocity, we calculate the mass flow rate to be approximately 7.95 kilograms per second. Now, to find the reaction force, we take that mass flow rate and multiply it by the difference in velocity between the outlet and the inlet. This actually gives us a recoil force about 89.6 newtons, which is roughly 90 newtons pushing back on the firefighter. Next, we are going to apply Bernoulli's principle to understand how the pressure changes as the water speeds up. It shows that the pressure at the inlet is higher than at the outlet. After plugging in the numbers, we calculate a pressure drop of around 119 kilopascals, meaning a large amount of energy is converted from pressure to velocity. Now, let's look at some dimensionless numbers used to describe the type of flow. First, the Reynolds number. This compares inertial forces to viscous forces. Our value comes out to over 400,000, which confirms that the flow is turbulent. Next, the Mach number, which compares the speed of the flow to the speed of sound. With a flow velocity of 16.22 and a speed of sound of 1500, the Mach number is about 0.011. Since this number is much lower than 0.3, we know the flow is incompressible, which is typical for liquids like water. Lastly, the Froude number. This actually compares inertia to gravity. Using the velocity and representative length, we calculate the Froude number to be around 10.3, which tells us the flow is inertia dominated, meaning gravity has little effect on the motion. In summary, The fire hose nozzle clearly shows how fluid mechanics applies in real life, from velocity changes and pressure loss to force generation and flow behavior.
Encountered problems. Although the nozzle is effective, there are several real-world problems during use. First, the recoil force we just calculate almost 90 newtons can destabilize the firefighter without proper stand or support. This may lead to injured or poor aim. Second, hose can kink or bend, especially when quickly deployed. This disrupts flow, reduce pressure, and cause turbulence inside the hose. Third, during extended use, especially under high pressure, the nozzle can experience localized overheating. Although rare, it can degrade performance. Lastly, holding a high pressure nozzle for a long period causes muscle fatigue, reducing the effectiveness and safety of the firefighter.
To improve safety and efficiency, we propose several upgrades. First, we use counter recoil stabilizer like tripod or recoil absorption mount. This reduces the force on the user, so the user not get dragged back. Second, install flow rate regulator to maintain consistent output even when supply pressure varies. So we know that the flow rate of the water is still same, even though we use different shape, different nozzle. Third, action the design with ergonomic pad grip to reduce wrist fatigue and improve maneuverability. So when we grip the hose, so we can easily to control it. And finally, consider smart nozzle. Equip the system with sensors to monitor pressure, temperature and flow rate in real time. This can aid both training and live operations.
In conclusion, the fire hose nozzle is a powerful and practical demonstration of momentum flow analysis. This study of a fire hose nozzle under the lens of momentum flow analysis demonstrates the practical application of fluid mechanics principle. Through calculation and theoretical understanding, it is clear how high velocity fluid flow can generate substantial reaction force. Addressing this through design improvement ensures safety, performance, and reliability in firefighting operation. Understanding this mission allows us to design better systems that are safer, more efficient, and easy to use under extreme conditions. Thank you for your attention. Now, a video will be played to educational purpose.
You've probably seen it before, an out-of-control fire hose and someone trying to get a hold of it.
Some parents may say that it's similar to what they have to deal with when their kids are on a sugar high. But the incredible power seen in a loose fire hose is due to the high velocity and flow rate of the water exiting the nozzle.
It's the velocity that allows the stream of water to travel a long distance so the firefighters can maintain a safe distance from the fire.
And most of us know that using more water at higher flow rates would be faster at putting a fire out.
There are two factors that affect the velocity and flow rate from the fire nozzle: the pressure of the water entering and the nozzle design itself.
Akron Brass is a company that designs a variety of equipment used in firefighting, including nozzles.
We spoke with Ajit Singh, a senior engineer there, to understand the operation and design of the assault nozzle.
Ajit explained that some past nozzles were designed to ensure a constant pressure water flow, no matter how much water was being pumped through.
That nozzle design is called automatic. They have a spring-loaded baffle mechanism at the exit to restrict the water flow.
The spring allows the baffle to open more if there's an increase in water supply to the unit, maintaining the pressure while allowing more water to flow through.
Their main advantage is that the adjustable opening provides a steady stream flow pattern with varying water supply conditions.
But fire crews encounter different water flow conditions at each fire scene. A traditional automatic nozzle may shoot a water spray that looks good, but could severely restrict the amount of water flow in case of a pressure drop.
In this case, the amount of water in the spray may actually be very different, leading to some risk for the firefighter. That's why Akron Brass designers came up with a fixed baffle design.
This ensures that the controlling gap at the baffle remains constant, and a pressure drop will not cause a severe decrease in the amount of water flow.
To allow a fire crew to use the nozzle for a variety of locations, the baffle is interchangeable, so the fire crews can match the nozzle to their desired water flow to get an optimum stream quality.
Ajit and his team used CreoDirect modeling to quickly develop different geometries for their baffle designs. They could then import the designs into a computational fluid dynamics program to simulate the flow and determine which ones provided the best stream quality.
This saved them a lot of time and expense compared to creating many prototypes and testing each one.
Modeling also helped in ensuring that the unit was robust enough to handle water pressure of up to 250 psi and flow rates of up to 350 gallons per minute.
This while keeping the unit light and easy to operate, since some fires can take hours to extinguish.
You can see CreoDirect modeling in action. It's the same software that Akron Brass used to design the assault fire nozzle seen in this episode. Just go to ptc.com/go/modelingpe.
If you like the show, please give it a like on Facebook, subscribe on YouTube, or give us a rating on iTunes. We'll see you next week for more great design engineering.